we started to discuss separable extensions. So I think we should continue about separable extensions. Separable extensions. We have defined them as certain extensions. So we call a field extension L over K. We call separable if all elements of L are separable over K. Yeah. So it's separable. By definition, if any element of L is separable over K. Yeah, and we have to say what is this, and this by definition this means that minimal polynomial, the minimal polynomial of y, of alpha over k doesn't have multiple roots, so it has only simple roots. Simple roots, yeah. And so what I'm going to do right now is to discuss another definition of a separable extension, namely so in some differential terms, you probably remember that last time we discussed that actually to check that an irreducible polynomial doesn't have multiple roots, you just have to take. So what does it mean that the minimal polynomial doesn't have any multiple roots? It means that it is coprime with its derivative. Yeah. So it is, and this suggests that actually there is another definition of separability in terms of derivations. And so let me recall you what is a derivation. So we consider some commutative ring, say with unit, with identity element. So let me be a commutative ring. We'll assume that it is with, so it is a unital ring, and we may, if you wish, we can consider more general situation when it is not just a ring, but an algebra over some other ring. So it is a ring homomorphism. Homomorphism. But please let me know if you all know this stuff. So do you know about something about Keller differentials? No? About what? Keller differentials. No? Okay, all right. Then I'll say what is that. So commutative ring with, yeah. So in the case when we don't have any b, you can assume that this is z. You know that there is any ring admits a unique homomorphism from the integers, yeah? Because if you want 1 to send to 1, then everything else is determined uniquely. Yeah, so we have such a homomorphism, and then so what I'm going to say is derivation of A is an additive map, maybe a derivation of A over B, maybe, yeah, over B, or if over Z, we don't need to say this, is an additive map from A to some A module M. That satisfies the Leibniz rule, yeah. So, do you know what is? Yeah, you probably know what is the Leibniz rule. It is. It says that if you take the product, some product, then it should be sent to what? To A times dB plus B times dA. Yeah. So it's the Leibniz rule. Okay, so example, yeah, and maybe I should say that. Well, of course, you know some examples, yeah, probably. For instance, if A is a ring of polynomials, then you can take derivatives, and this will be an example with values in A itself, yeah. But in general, we don't want to restrict ourselves to this A. But what I'm going to say that actually all derivations form a category. So derivations of A form a category in the following sense. So the objects are, well, they are just maybe derivations of A over B, yeah, over B. I'm sorry, I didn't say what does it mean that it is over B. So if we say over B, then we want that D of C is 0 for all C in the image of let's call it well, psi. Yeah, but of course you can imagine that for instance derivative, what is derivative of 1? Derivation of 1, yeah, you can imagine that this is 0, yeah, because well, why, by the way?
Because B, image of B can H1 if it's not 0.
No, you see that you have to prove this, yeah. So so what is d of 1? D of 1 is the same as d of 1 square, yeah, and by the Leibniz rule this is twice. It is 1. Well, maybe I should write 1 times 1 plus 1 times d of 1, yeah, and this means that you can cancel these terms, and so this means that d of y is 0, yeah, d of 1 is 0, and therefore d of all integers, well, if there are some, well, if the image of so the d annihilates all the images of integers. So the objects here, but if in general we have to impose this condition. So if so the objects are just derivations. So derivations from A to some A module, and the morphisms. So if we have a pair of derivations, so then morphism. Let's write it this. So from D to D prime, M prime. Morphisms are morphisms of A modules. So morphisms are so those A linear maps F such that this diagram commutes. So this means that such that so if we start with D and compose it with F, then we get D prime. Yeah. So this is so all the derivations form such a category, and the claim is that this category has an initial object. So initial object. So yeah.
What is a category?
A category. Well, a category is certain pair of data. So you have what is called objects. Objects. They are well. You just imagine that they are some kind of points, and besides the objects, there are morphisms. So the morphisms are what you imagine as arrows. So and for each pair of objects, there is some, well, say set. Yeah. If we usually assume that.
How would we actually define it on paper? So I just can understand this definition with points. So I got lost in the beginning. So
Okay.
in the beginning of this definition category.
Well, maybe we just actually all categories we are dealing with, they are categories of sets with certain structures on them. So this means that you might think of any object as a certain set with certain structures. For instance, it may be a set or a group or a module. Or a module over a fixed ring. Yeah, so, so for instance, here the objects are just derivations. Yeah. You just write. You think of this as just you can imagine what is this. Yeah.
Well, yeah, it's some just some map.
Yeah, some map. And then, so the point is that.
So I don't understand what is a category in sense of how is this connected with commutative diagrams? So what's the connection?
Well, you see that commutative diagram is just so you see that so I didn't say what is a category. Category is not just objects; it's rather morphisms. So because for any or actually you can say that it is something like the set of, well, it's not a set of morphisms. It's some. You see the problem that there exists no set of all sets. Yeah, you know such a problem. But you can say that you can consider the category of sets. So the objects need not to form a set. That's the technical problem. But you don't really need to deal with such logical complications. You just think of them as certain points, and what is more important, that between any 2 points, between any 2 objects, you have a set of arrows, which are called morphisms. And for any triple of objects, say x, y, and z, you have for each pair you have a certain set which is called morphisms from x to y, from this, and also you have morphisms from y to z. And then you have to so category means that you have what is called composition. So it's a map from the direct product of these 2 sets to the set of morphisms between x to z. Okay.
Also, we should say that there is identity morphisms for all objects.
Yes. So for each, so if you consider morphisms to the object from an object to itself, then you have to have a distinguished element which is called identity, and which has the property that when you compose this morphism with something else, in this sense, in the sense of this, so this actually this is a data. This is gamma x, y, z. Then it doesn't change anything. And of course, this composition should be associative, and well.
So this means that there are maps from x to y and from y to z. Then
you can come
maps from x to z. Or there are no.
Yeah, you see that elements here you consider as maps, as map from x to y, and maps here you consider as y to z. And
these sets are not empty.
They may be empty. They may be empty.
Well, in case they're not empty, then.
But the point is that you can compose composable arrows. Composable means that they end. One of them ends where the second starts, and so you see that this.
So that actually means that there are homomorphisms.
It's not just a map.
There must be an arrow between x and z, or not?
No, we don't know whether there are any errors. But even if this map if this set is empty, you should still have. You see that a product with empty set is an empty set. So and an empty set you can map to everywhere. So it's again an empty set is what is called initial object in the category of sets. Initial means that there is a unique map from this object to any other. Yeah. So what I'm, but actually, well, maybe it's not very important at this point, because I'm going to explain in a very in a rather explicit terms what we are going to call an initial object of this. So initial. So maybe I should write this. Actually, I write an initial, but actually it is always unique up to a canonical isomorphism. So it's I don't know whether should I say an initial object. It is so it's well, say let's call it O. Yeah, O is such that for any object X, there exists a unique morphism from this initial object to our X. Yeah. So this is definition, and so what I'm going to say that this category admits an initial object. So claim. Maybe we should call this, say, derivations. Yeah, derivations of A over B. So this is this category. So the derivations of A over B has an initial object. It is called differential. Differential. So it is a map from, of course, from A to something called Keller differentials. A over B. So this is Keller differentials. Yeah, and this actually this this object has a very explicit description, namely yeah. So what do we want from this map? First of all, this should be an A module, yeah, and it should be well, maybe I should start this construction. Да, что? Что? Над B, вот в этом месте. You see, the point is that we consider, if you know some, at least a bit of analysis, you know what is a differential of a function. So, and you probably know that differentials of a constant is 0. Yeah. So the point is that we consider B as the ring of constants. Yeah. So if, for instance, if there is no any B, then you just think of A as a ring of over the ring of an algebra over the integers, because integers are always mapped to any ring. Yeah? So the construction is so it's easy. You just span an A module using this. Well, you don't know what is D, but you just consider free A module generated by the symbols generated by the symbols dA for all A in A, but then you have to impose certain conditions to make sure that it is a derivation. Yeah. So how do you do this? So what does it mean that it is generated by the symbols? It means that you consider formal sums, formal finite sums, like what? Like AI, D, B, I, and then you mod out by some relations. First of all, you want these symbols to be additive in the coefficients and additive in this. So you want this symbol to be additive in A. Yeah. So modular relations. So the following. So additivity first of all. So A plus A prime dB is A dB plus A prime dB. Next, it should be additive in B. And of course, and that's it, more or less, in the following sense. dB prime. This is B additivity in this. Next, you want the Leibniz rule. So the Leibniz rule is what? Leibniz rule. So it is A dB C minus, yeah, it should be the same as AB dC plus AC dB. Yeah, and finally you want the image of B to be a constant, yeah, to have a zero differential. So AdB is 0 for all B in the image of B. Yeah. So just maybe you may think of this that it is too complicated in the sense that there are too many this formal sums who form a huge module, but actually the situation is much easier in the following sense. So if A is generated by a set S. So for instance, this set may be even finite, yeah, unlike the original A, over a set S as a B algebra. Then the differentials is generated by the elements ds, where S runs over this set as an A module. So why? Because what does it mean that A is generated by a certain set S? This means that any element of A can be presented as a polynomial in the elements of A, elements of S, and so this means that any element of A is a polynomial over B or over its image in elements of S. Yeah, and then this means that for any element A, yeah. So and this means that dA. So не видно? Что там? No, yeah, and so A is a polynomial, say P of S1 and so on, Sn, yeah, and then you can write this, write a differential, yeah. So differential is just you take partial derivatives, so it will be a sum over some P. Well, I write as usual because. Well, you can imagine what's that, dxi dsi, yeah, so I from 1 to s. And you see that we have expressed everything through differentials.
Perhaps it's dSi.
No, you see that a polynomial is just a formal expression, and we have formal derivatives. So it is again a polynomial of lower, in a sense, of a lower, yeah, maybe not in a sense, but always of a lower, well, in some sense, because we have many variables. Yeah, so it's again a polynomial, it's again a formal expression. But in this formal expression, we substitute the indeterminants by these concrete elements. So we get a concrete element. So this is an element of A, and any. So the conclusion is that any differential becomes. Maybe I you see that maybe I should write here big D instead of small d to make sure that it's not important what is this derivation. Yeah, so because it's always true. You see, we don't care what kind of derivation.
Well, we define the initial test.
No. You see that. No, wait. For any derivation, one has this formula. Yeah. So it doesn't matter which derivation do we consider. Okay. So yeah, and yeah. So we have this module. Maybe I should give some examples. Well, examples you can imagine maybe by yourself. For instance, from this description. So maybe you can say what is so example.
If we take just polynomial algebra, we will
Yes.
get just free model.
Yes. Yes. So if you take, so we have a polynomial algebra. So what do we get?
Free model equated by x.
By dx, yeah.
Yeah.
So it is. It will be. It will be not just a free model. It will be a free model of rank 1. Yeah. So it's generated by one element, because you see there are free models of rank 2, 0, and so on. Yeah?
Do we have one variable?
You want several. Okay. 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 You mean that if we have several variables? Yes. If we have several variables x1, x2, and so on, then you are completely right. It will be indeed. Maybe let's call it B. Yeah. Let's call it B. Then it will be, and this will be A. This will be A dx1 plus you see that if there are infinitely many variables, then this will be so you see that you cannot consider this as a product, but this is a sum. Yeah, so this will A dx1, x dx2, and so on. Okay. All right. Yeah. So maybe some other example. What happens if our extension is not free like this, but rather, for instance, if B is a field and A is a finite extension. So that's what I'm sorry.
You mean A field and B?
Both of them. Yeah, maybe I can. Yeah, maybe we should. Maybe you can say why this is universal. Yeah. So can you say this?
Because every differential just
Yeah,
matters.
satisfy. Yeah, it should satisfy this relation. So yeah, but how do you construct? So you see that to show that this is universal, you have to. You see, we have a concrete derivations. This one, and we have an arbitrary derivation to a modulo m. So how to construct this? How to construct this morphisms of morphism of A modules?
So we just send D images dA to big DA.
Yeah, that's right. So it's completely, in a sense, it is a tautology. Yeah. So and just yeah, and of course this is unique and so on. All right. Then yeah. So now we come back to the fields, and so if A and B are fields, for instance, if you see that any field is generated, any finite extension is generated by finitely many elements, yeah, and each. So suppose that L over K is a finite extension, a finite field extension, yeah, and so the question: what are differentials? Of course, you may say that L it is a finite extension. Yes, so actually L is generated by certain elements, theta 1, theta 2, and so on, theta n. Well, but we may, yeah.
L over K is which extension?
A finite field finite extension of fields. Конечное решение полей. Yeah, we may assume that for simplicity that it is generated by a single element.
So also we assume that we look at polynomial combination. I mean, because it is finite extension. I mean, with such braces, we assume that we look at rational combination in some sense, but we can just treat as polynomials in that modulo sum.
In principle, you are right. Yes, yes. You mean that if it is generated by theta, then it is k plus k times theta plus and so on plus theta times degree minus 1. Yeah.
Yeah.
Something like this. Yes, you can think like this.
I mean that maybe it will be simpler to understand what is Kerr differentials if we treat extension as a quotient of polynomial ring.
Yeah, yeah, yeah. Actually, actually, what you're saying is that if P is a minimal polynomial, of theta, then, of course, by definition, well, by definition, P of theta is 0, yeah? P of theta is 0. But you know what is the differential of 0? What is differential of 0? Yeah, so it is 0. But what is differential of a polynomial? No, yeah, it's derivative. It's derivatives times the differential of the element. Yeah. So what does this mean? This means that derivative annihilates everything. So, and now we have two options. As this is a field, we have two options. Either this derivative is 0 or non-zero. Yeah, because if it is non-zero, then it is invertible. So the conclusion the extension is separable if and only if the differentials vanish. Yeah. So if and only if L over K is separable. Because you see that the derivative can be 0 only if the minimal polynomial has multiple roots. Yeah? And this is definition of the separability. But you see, here you have to be careful because we should really assume that this extension is finite. Because you know that if let me give you one more definition. So you maybe you already know this definition. A field is called perfect if any algebraic extension of that field is separable. So a field K is perfect if any algebraic extension of K is separable. So can you give some examples of perfect or non-perfect fields?
Rational numbers.
Rational numbers is perfect. Is perfect. Okay. And more?
FP.
FP. So why this is perfect? Maybe you can generalize this.
Because it have characteristic 0.
Yeah. So actually, any field, any field of characteristic 0 is perfect. Yeah, of course, because any extension of a field of characteristic 0 is separable. Yeah. Okay. So FP. Why FP is perfect?
Because Frobenius automorphism on all algebraic extension is surjective.
Yes, but can you say this in more add some details of argument? Because you see, so the point is that we so I mean the problem it's not evident what is the relation between Frobenius and perfectness.
If we suppose that we have inseparable element which is not separable over FP,
Yeah, so you mean that, so, yes, so if alpha is not separable,
Yeah, we can look at its minimal polynomial.
yeah, so P is a minimal polynomial of alpha, yeah.
Then by induction, we can see that if we have zero derivative, then P is polynomial of x in power P in power some n.
Yeah, so if P is so if yeah so if P prime is 0, then P is Q of x to the P. Yeah, okay.
I mean, we can proceed by induction down because we can have not P, not just P, but some power of P.
Yeah, wait. So actually, what you're saying is that if so, this is a polynomial over fp. Yeah.
Yeah.
So so it's a polynomial over fp, and therefore it is itself a pth power of yeah.
I mean, if Frobenius is surjective, we can just find
Yes.
the roots.
So yeah, but okay. So then you, yeah. So actually, what you're saying, maybe we should write another way. Yeah. So if it is, so what you're saying is that actually there are two kind of perfect fields. So the first one is of characteristic 0, and the second, so K is of a characteristic P which is positive, and any element of K is a pth power. Yeah, because so what you're saying is that you can, if derivative is 0, then this polynomial is a polynomial in the pth power of x, and as any element of K is a pth power, you can find an element or a polynomial S such that this polynomial is in x to the p is pth power itself. Yeah, and therefore it is not so it is S is a polynomial of k, and so it is not irreducible. Yeah, so that's a contradiction. Yeah, so yeah, so actually this is yeah, but so we have two kind of examples, but the question is whether there are some other examples. So other means that a field can a field of positive characteristic be perfect if some element of this field is not a pth power. So alpha is
So we can try to treat extension by x power p minus this element. I mean, add this power and
You mean the pth root?
yes, and prove that it isn't separable.
Yeah, of course. Yeah. So if it is not pth power, so we can just consider this extension x to the p minus alpha. Yeah. So of course this is an extension. So maybe also theta. So theta to the p is alpha, and of course you see that this this extension is not separable, yeah, because the minimal polynomial has zero derivative, yeah, because so the conclusion, so this is a complete list of perfect fields. Yeah. Complete list of perfect fields. Okay. Now, but what I was going to ask you is what are Keller differentials if K is perfect?
So the complete list of perfect fields is consists only of fields of characteristics 0.
And those fields of positive characteristic P where all elements are pth powers. So what are differentials on a perfect field? Sorry, a perfect of positive characteristic P. It is important, of course. I'm sorry, because yeah.
You mean over
Over nothing, over Z.
Okay, we can suppose it's 0.
Why?
Because 0 is about separability and perfect fields also.
I don't understand.
I mean, we have conclusion that for separable extensions.
No. You see that if it is yes, if this extension is separable and finite, yeah. This is here we assume that that this extension is finite, and assuming this, we conclude that vanishing of Keller differentials is the same as separability, but only assuming that this is a finite extension.
So, okay, we can try to treat some example rational functions of one variable over fp.
Oh, by the way, is it a perfect field?
No, because the variable doesn't have path root.
Yeah, so it's not perfect. Yeah.
Okay.
Yeah, so maybe it's you see that we assume that this characteristic is positive. This means that any element is a pth power of something. Yeah. So what is derivative or derivation of pth power?
0.
0.
So it should be 0.
It is 0, yeah, because for any A alpha in K, there is a beta in K such that alpha is beta to the pth power, yeah? And therefore d alpha is 0 for any alpha. So just to explain that you should be careful with this, because it works only if this differential criterion works only if extension is finite. Okay. Now, so we have defined. We have discussed some versions of separability, and now we have to relate Galois extensions with normal separable extension. Yeah.
Can you provide example of some extension that a perfect field itself, but not separable as extension over something?
Yeah, you just take any perfectization. So, for instance, yeah. So take any. So, for instance, K is a perfect field. Perfect field. So some positive characteristic, and take rational functions in x to the pth root of x root number p square, and so on. Yeah. You see? So of course they are huge. But or if you wish, you can consider some. I think Peugeot series, for instance, like this. So you can. Well, the same thing, but with certain restrictions when you have. Okay. Yeah. So yeah. Now coming back to Galois extensions. Wait. We have to. Yeah, we have to relate just to make picture more complete. So we have to relate Galois extensions to normal and separable. Yeah. So actually, the claim is that. So this will be. The claim that actually Galois extensions is the same as normal separable extensions. Normal separable extensions. So why? So first of all, let me recall you that what were our Galois extensions? They were they were coming from a pair consisting of a field and a finite group of its automorphisms. A finite group of automorphisms of L. And we call, so if we put denote by K the fixed subfield, we call L over K a Galois extension. So first of all, why is this extension normal? So first, so K is normal. Why?
Can you remind us what is a normal extension?
A normal extension is a splitting field of certain collection of polynomials.
Thank you.
Normal, yeah. So splitting field, splitting field of a collection of polynomials. Or there were several equivalent actually definitions. For instance, we call an extension normal if any irreducible polynomial becomes so for instance, if an irreducible polynomial gets a root, then it splits completely. So if an irreducible polynomial over K gets a root in L, then it splits completely. Maybe this definition will be more useful. Yeah. You see? So yeah. So maybe with this definition, it is easier. So so we have to check that any. So we take an irreducible polynomial over K.
Can you just take all elements from L and not from K, and state that L is splitting field of all these elements, because we have because minimal polynomials is just the product of x minus alpha, whereas alpha from orbit by action of J. Does it work?
In principle, this is true. But why should you distinguish the case where they are not, where they are? Why don't you like that they are in K?
Maybe we should be distinct. Yes.
Mm-hmm. Yeah. So yeah, in principle you're right. You can just. But wait, we have to prove this. Yeah. So as an idea, it should work, but we need some details. So if you wish, to use this definition, a collection, let's call it S. So let S be the set of all of what? Of
all minimal polynomials.
All minimal polynomials of elements of L. Okay. And so you claim that all these polynomials split completely. Yeah. Why?
I suppose that minimal polynomials.
So yeah. So we take some minimal polynomial p. So p of theta, for instance, is 0. Why does p split completely?
I hope that P is just product of x minus sigma beta or sigma just transfer G.
Actually not, because because you see that G is of order something, but theta may be already in K, yeah?
But we can treat just different
Yeah, so you have
stabilizer.
by stabilizer, yeah. That's right. Yeah, so you don't distinguish elements that differ by a stabilizer of theta, yeah? Yeah, and of course this is why this is
G, the whole group stabilize this polynomial, so it has coefficients in K.
yes, so yes, so the coefficients, yeah, so the coefficients are fixed by G, and therefore what? Therefore they belong to the fixed field, and the fixed field is K. Yeah. Right. All right, and yeah. So this is this explains that this extension. Yeah. So, but why is it minimal? Yeah, because of course, because we have such a multiple. Yeah, we should have a multiple x minus theta, and as this polynomial is invariant under G, it should have multiples x minus theta to sigma for all sigma, yeah, in G. So yeah, so we have all these multiples, and this is what we want because the coefficients are in our base field.
And so coefficients are fixed, and then the last.
You see, so we want. You see that what do we want? We want a polynomial that vanishes at theta, and
I just don't understand what's written on the last line.
that the fixed that this coefficients belong to the fixed field, fixed subfield. Okay, so can you say it again?
Why is it a minimal polynomial?
Yeah, so first of all, it is a polynomial over K, do you agree? And it has root theta, and it should have all roots in the G orbit of theta, because you see, when you it should be a product of x minus theta with something. Yeah, and it should be invariant.
We can just say that okay, we have P that vanish theta. So a minimal polynomial should divide p, but all roots, okay, if it divides, it doesn't matter because all roots already
No.
in L. We can just take, sub-polynomial.
No. Maybe the question is why this is the minimal polynomial. Why there are no polynomials of lower degree, for instance. But the answer is that as its coefficients are in the fixed field, then it should contain all its root. Its root should include all elements in the orbit of theta. You see? So, so theta is a root. So x minus theta divides p, and therefore, well, maybe p minimal, yeah. And therefore, x minus theta sigma divides the same p minimal, just because it is G invariant, fixed by G. You can write here sigma. You can write here sigma, but this is the same as all right. So this is normality, and now we have to check the separability. So again, we know that so why?
But we already have minimal polynomial, and we see that it doesn't have multiple roots, no, because all roots.
Yeah, but you should be careful a little bit, because you mean that okay, yes, you say that you say yes. Separability is trivial, yeah. So the separability is trivial because all yeah. So we don't have so it does not have multiple roots. And this implies this separability. Yeah. So now, what is more, maybe less evident, is why this is the same. So now we have a normal separable extension, and the question is why. So yeah, so we assume that it is a normal separable extension, and the question is why is this a Galois extension? So we need to show that the base field is indeed a fixed field of certain group, and so far we don't have any automorphisms. We should construct them. Well, maybe not constructed, but at least we have to show that there exist sufficiently many automorphisms that give our Galois group. Yeah. So so we assume that LFK is normal separable, and separable. So, and how to show that this is this is a Galois group. This is a Galois extension. So we need. So of course we can consider the group of automorphisms, yeah, G of all automorphisms, but in principle this group may be even trivial. Yeah? So the question is, why is this
maybe we should try look at the invariant subfield by action of this group and take some element from it.
Okay, so you propose to take an element fixed by G, okay,
Which doesn't lie in K.
okay,
And treat extension K with alpha.
so you consider K of alpha over K, sorry.
Okay, we should prove that minimal polynomial of alpha of degree 1.
Yeah, so you consider the minimal polynomial of alpha. Yeah, so what is this? So P of x is the product of some x minus theta I. Okay, and so we know that all theta I, theta 1, theta n are pairwise distinct. So yeah, so it is and so what? And maybe theta 1 is alpha, yeah? Theta 1 is alpha.
Excuse me, what was the theta 1?
Just roots, yeah. You see, you see that our extension is normal, yeah. So so any
where was this? Okay.
yeah. So and this polynomial has a root.
Understand your handwriting.
Ah, sorry. I'm sorry. Distinct. Yeah. Okay, so can this happen?
Maybe we should look at automorphism of these extensions and
We could take an element from the group and simulate that to the polynomial. It shouldn't change it because this polynomial has coefficients in K, which is a subset of the invariant field. So what it does to the vectors, it just switches them somehow.
Yes, but you are completely right. But there is one essential point which you didn't mention explicitly, namely that when we discussed normal extensions, we mentioned that you can always send any root to any other root. So the transitivity, yeah?
oh, so we can treat splitting field of pair?
already, you see, we can forget everything. We can forget everything. We deal with this, with the splitting field of this polynomial. It is a subfield of L, and it is, again, it is normal, it is separable, and actually we don't even need separability as soon as we know that these elements are pairwise distinct. Then we only use.
So we have.
So that's it, because so
Do you know that we can extend this?
we don't need to extend anything, because we already know that on in the normal extensions they exist automorphisms sending any root to any other root. So this means that theta 1 is not fixed if there are other roots. So let me write this. So for any, well, there exists an automorphism, of L over K, sending theta 1 to theta 2 if n is greater than 2. Yeah, and this is contradiction, because theta 1 is fixed by the group. Okay, so so now we know that Galois extensions are the same as normal separable. And by the way, yeah, so far we have defined only finite Galois extensions, but actually later we will consider, maybe we will consider infinite extensions, and for infinite extensions this is again true, so you can think of Galois extensions as, so far, you can think of them as normal and separable without finiteness condition. So it's in principle, you can, maybe I should write this definition right now. So definition, an algebraic. Maybe I forgot. Actually, have we defined only finite Galois extensions so far, or arbitrary? Do you remember? Only finite. Finite. Okay. All right. Then let me define an arbitrary. So an algebraic field extension L over K is a Galois extension. If the same condition if K is the fixed field of this group. Yeah. So it's so we don't have any.
So this group is consists of automorphisms identical on K.
Yes. Yes. But you see that the only condition we impose is that this extension is algebraic, because sometimes people consider arbitrary, but it's not, it's something different. Okay, so yeah, so now we have defined separable derivations. Okay, now maybe we should discuss one more.
We're running out of time.
We don't have time.
We're running out of time.
Okay. Maybe then maybe questions are. By the way, I have a question. So I asked you, whether we can meet. There are some people that are abroad, so maybe we should make an extra session online. Do you have any preferences? Some people suggested to meet at on Fridays, yeah. But the my only problem is that there is a seminar of algebraic geometry, laboratory of algebraic geometry. So from time to time I would like to go there. But so if we could shoot, does anyone have some classes before this? I don't remember when. 4:20 p.m. I think. Does anyone? Нет? То есть можно? So, что, Маш?
В 4 предлагается?
Ну, в 4, да.
В 4 у меня семинар в 4. Сейчас
А.
я проверю еще раз.
Ага.
Я чуть запуталась.
А что у нас будет на добавке? То есть просто продолжение?
Ну, да, продолжение. Может, что-то будем разбирать, потому что мы пока что ничего не разбирали.
До 4:10.
До 4:10. Ну, конечно, можно. Ну, можно.
Вот эти вот занятия онлайн потребовались. Действительно много народу уехало, видимо.
В смысле, по средам тоже?
Да.
Записи же есть?
А что, если на 10 минут меньше будет, разве это критично? Я просто...
Не, ну хорошо. Можно и. Не, ну, в общем, тогда что? Тогда, ну, то есть сдвинуть не получится, да, то есть скорее 16:20, да, то есть там, ну там.
Ну, я приду, наверное, типа 16:20, то если...
Ага, ну хорошо.
Если первые семинары, а не...
По пятницам.
Ну, по пятницам.
Наверное, потому что там как бы нужно, чтобы, наверное, что-то было.
Так, это типа просто часть программы или это для задавания вопросов? Вот таких вещей?
В общем, да, это
Ну, я бы сказал, что... ну это
то есть,
интересный
это,
вопрос.
это у нас будет просто как второй семинар в неделю, такой стандартный, или же это будет как консультация скорее?
Я бы сказал, что второй семинар в неделю, потому что, кстати, кто-нибудь видел, появился доступ к видеолекциям? Обещали, нет?
Я на ютубе прошлую видел.
Ну, в смысле, видеолекция на
Нет, Катя, там в принципе это заявлено как по-моему, я уже не помню как семинары, при том, что видеолекции, они как бы уже есть, они записаны там на курсере.
Они курсеры скрипсировали,
Да.
Но вроде бы это должно остановиться на вот вышкинскую систему.
Да.
Вот,
Но этого не случилось.
Ну, в общем, надо сходить в учебную часть еще спросить, но это не от них зависит, это зависит от
Ну, я понимаю.
большой вышки.
Да. Ну, в общем, нет. Ну да, я просто говорю, что поскольку видеолекции нет, то, казалось бы, ну, что нам остается делать? Ну, добавить еще. Вот. То есть, еще раз, если у вас есть какие-то конкретные предложения, я готов их обсудить. Вот. Но я бы там в качестве начальной точки предложил это просто как дополнение к тому, что происходит по средам. Вот. Но если возражений нет.
То есть просто как логическое продолжение.
Ну да. Ну,
если можно, типа, первые 20 минут делать просто обсуждение вопросов.
Да. В смысле, что вы там не будете успевать. Хорошо, я понял.
А в понедельник? Да,
Пятница.
Просто у нас еще вроде понедельник был достаточно популярный.
Понедельник был. Там проблема, это я там все перепутал. Там у меня в это время какая-то пара. Вот. А потом уже этот понедельник становится страшно непопулярным, насколько я понял, потому что никто не пришел. Там вот, по-моему, кто-то один пришел в прошлый раз и удивился, что никого нет. Вот. Так что понедельник, наверное, не получается. Так что, против пятницы нет даже? Yeah, so I'm sorry, just we have some technical. So we are discussing an extra session, maybe a little bit shortened on Fridays. Yeah, so I'll make an announcement in Google class. Yeah, but roughly speaking, it will be about 4 on p.m. or 4:20 p.m. On Fridays.
It's maybe for 20, just for all of us.
Okay. Oh, maybe there is a good point about 4:20 because
Fit in timetable.
yeah, because we I think for the Google Meet, if actually I'm not sure that it will work, but for the Google Meet we have 1 hour for free. But the problem is that sometimes it doesn't work. Yeah.
Like, unlimited.
Sorry.
We had we had some meetings in Google Meet, and they lasted for about 2 or 3 hours.
For how many people?
Around 5 or 6.
5 or 6. Oh, okay, all right.
Так, вопрос, не надо трансляцию отключить.
Нет, ну может быть кому-то интересно. Там, наверное, можно вырезать. Все, что